Hello everybody, today we're going to be talking about factoring the difference of squares. Now the difference of squares is when you have a binomial with two perfect squares and they're being subtracted. So if it's the format is a squared minus b squared, like up here, you will always see this as factoring a plus b times a minus b. And it doesn't matter what comes first. It could be plus first or minus first. It doesn't matter. So look at this first one here, x squared minus 25. Notice there's two perfect squares. X squared is a perfect square and 25 is a perfect square. Since those are perfect squares, what I do is I take the square root of each thing and then I just utilize this formula. So the square root of x squared is simply x, and that goes in these first spots here. The square root of 25 is 5, it goes in the second spot. And then I just need one to be plus, one to be minus, and it doesn't matter which is which. This is how x squared minus 25 factors. Look at the next one, 36 and 25x squared. Okay, we'll set up our answer first. Square root of 36, 6, that goes in the first spot here. Square root of 25 is 5, but notice there's an x squared with it, so the square root of x squared is just x. So 6 plus 5x, 6 minus 5x is the factored form. Now look at number 3, it's a little bit different. Notice 3 and 48 are not perfect squares. However, and actually I think we had a typo here. This should be a third. Okay, so let me write this again. 3x to the third minus 48x. Okay, first thing we're going to do is look for a greatest common factor. We got 3 and 48. So I can factor out a 3 first. There's also an x cubed and an x. There's an x we can take out of both. Now, factoring, another way of thinking of factoring is dividing. You're factoring out, you're dividing out. So we're going to divide each of those things by 3x. We're left with x squared and 48x over 3x, 16. Notice what we have left. We have x squared minus 16, the difference of squares. The x squared minus 16 can factor into x plus 4 and x minus 4. Pretty much like the previous two problems. So I'll do x minus 4 and then I'll do x plus 4. But because we factored out a 3x, that has to stay part of the problem. Just like that. There we go. Back up to number 4, we have 16x squared minus 49. Look at the perfect squares. They're both 16 and x squared, 49, perfect squares. We'll set up the answer here. 4x minus 7, 4x plus 7. Notice I get the 4x and the 7 by taking the square roots of each of the two items. That's the factored form of that one. Now, look at number 5, x squared plus 9. Yes, those are perfect squares, x squared plus 9, but notice it's a sum, it's an addition. We cannot factor that, so we say it is prime. Similar to like a prime number, its only factors are one in itself. If a polynomial cannot be factored, you call it prime. Finally, we have x to the 4th minus 16x squared. Let me write this out so we see the exponents a little better. X to the 4th minus 16x squared. Now, it's true both of these are perfect squares. Okay, so we could factor the way they are right now, but first let's look for a GCF, just like in number 3 here. Look for number GCF, x to the 4th and x squared. We can take an x squared out of both of them. And then we'll write what's left after dividing out an x squared. This would be x squared, this would be 16. Alright, and keep in mind we can always check. We can always check by redistributing this if we wanted to. Notice if we redistribute, we would have x to the 4th minus 16x squared. But look what's inside the parentheses, difference of squares. x squared still there, but we turn x squared minus 16 into x plus 4 and x minus 4. And there's our factored form. Thank you for watching.